Okay, so the goals of this subsection are to extend our knowledge of kinetics, the rates of reaction, to this idea of how far does the reaction proceed, especially when it's reversible. So where is the balance point in the reaction going forward versus the one going in reverse? And those are called equilibrium systems. And so being able to describe those and then understanding the dynamic nature of them, of a system at equilibrium. So chemical equilibrium is this really important idea that helps us understand the extent of a reaction. By extent, I mean, if we add a bunch of stuff to a reaction vessel, is it going to proceed to 100% or all reactants get converted to products? That might be our intuition from what we know about chemistry so far, but the reality is probably not. It's going to stop before it reaches 100% for most systems, and it's going to reach an equilibrium state. So equilibrium in chemistry is defined as when the rates of a forward and the reversed part of the same reaction are equivalent. And we talked already a little bit about how we think about these reversible type reactions. So a reversible reaction is denoted by this double arrow here. And the example I'm talking about in this case is this decomposition of this molecule N2O4 into two of these NO2 molecules. And I've got a couple figures here to represent this. The one on the top is sort of a molecular scale view of tubes. These are little glass ampules where the system has been charged with N2O4, and the one on the far left is at time zero. So you can see all you have are N2O4 molecules. You let this thing just go once you allow the stopwatch to start. And you start to see the appearance of, after some period of time, some NO2 and some N2O4. And then after some period of time, nothing changes. And you end up with some ratio of both of these, the reactant and the product. And I should say that the words reactant and product are sort of nebulous once you start talking about reversible reactions, because they're all about perspective. In the way that I have this written here, N2O4 is a reactant, and NO2 is the product, but I could easily just write this in the other direction and those terms would be flipped. And so it's important to know that most chemical reactions are reversible, which means that they all are capable of achieving an equilibrium state where the forward and the reverse reactions are equivalent to. What does that look like graphically? Well, this is a nice representation to illustrate what chemical equilibrium really looks like, and it points to what's happening in the schematic up here. So in this example, we have only N2O4 present initially, so only the reactant in the reaction as it's written, and we have the concentration noted here and time. And so you have two colored traces, one for NO2, which is pink, and one for N2O4, which is blue. And what we see is if we start with 0.04 molar of the actual N2O4, that's should be sitting right there, that it's going to slowly get decomposed, and as it does, you're going to see the growing in of this other species, the NO2, and you're seeing that grow in with a stoichiometry of 2 to 1. So you're getting twice that for every 1 mole of N2O4. More importantly, what you're seeing is if we start with 0 NO2 in the reaction chamber, we start to see more and more and more of it being created, and that's in response to some of this being destroyed. And at some point, which is noted by this dashed line, the concentrations of those two things don't change anymore. And that's what's noted in this portion of the schematic. The ratio of N2O4 and NO2 are exactly the same, doesn't change. But what's important to know, and I should say this is the moment we are at chemical equilibrium in the system, because the concentrations of both these species are exactly the same at any given moment in time. What you would observe with your eye for a system in chemical equilibrium is no macroscopic change. Nothing's actually changing. It looks the same because the forward and reverse are happening at exactly the same time, so the concentrations of those species are unchanging. What's super important to know, though, is that this process is dynamic, and that's why you often hear equilibrium called dynamic equilibrium. The idea behind dynamic equilibrium is that these systems are still reacting. If we go back to the definition of chemical equilibrium, that state is achieved when the rates of the forward and reverse reaction are equal. That implies that these things are still reacting, but they're reacting in a way that the forward and the reverse are exactly the same speed. And so if you were to zoom in to the molecular scale, you would see that N2O4 is being destroyed at the same rate that NO2 is being created, which is a dynamic process. But if you zoom back out, you wouldn't see any change to the system. And that's a real key characteristic of chemical equilibrium, is the macroscopic observation means it's unchanging, it's at equilibrium. The microscopic one means, though, it's still dynamic. It's actually alive. Things are happening, but they're happening in equal. So now I'm pasting in the same plot that we just interpreted on the left with one that's slightly different in its starting conditions on the right. So notice that the one on the right, only NO2 is present initially. And so your intuition before understanding chemical equilibrium and reversible reactions may be that, well, if I only have NO2, then nothing's going to happen. But since this reaction is reversible, it is going to reach the same equilibrium state as if you started with a bunch of N2O4. So we start down here, or we start up here with NO2 at 0.08, and as this stuff gets destroyed, we are running this reaction in reverse, and we start to create N2O4. These two curves start to intersect, and voila, at the same point, we start to have unchanging concentrations of both of these species, and that's because, again, the forward and the reverse reactions for this reaction, which I'll write as Kf and Kr, those two things, well, let's just say the rate forward is equal to the rate in reverse, and that's what gives rise to this equilibrium state and this equilibrium state being identical. Because the rates are unchanging regardless of what you start with in the chamber. They're going to reach the same equilibrium position. It's important to know that the equilibrium position can be affected by external perturbations, like always. So we could change the temperature, we could add other stuff to the system. That's going to take us into this new idea of how do we perturb what the extent of the reaction is, because in some circumstances, this isn't good enough, right? Maybe you're trying to make fertilizer to feed the world. You don't want a reaction that only proceeds to halfway. That's a pretty inefficient way to do it. So what can we do as chemists, understanding chemistry, to get reactions to proceed beyond where their equilibrium point might lie, which might not be at completion?